But now we get to the idea of multiple flows on the network, and you can think about this as different items that need to go from place to place on a truck, different groups of people in the subway, factory that needs to move several different kinds of components to different things. And one of the difficulties of this kind of problem is that all of the flows have to share the same capacity. So if one flow uses up capacity, the other flow can't. And one flow can block another flow because of this shared capacity. Now there are some existing techniques, but there's a restriction on them. What that you can do is you can tell them, I want this flow to be this value, this flow to be this value, this flow to be this value, and it can tell you, yes, here's a thing that does that, or no, there isn't. And if it gives you no, it doesn't give you any information about how close you are. So it would be nice if we could get some more information. And one of the things that would be nice, most likely, is to expand flows. And let's think about this. The way that flows are now, we're restricted by how big the capacity is. We can't put more flow across an arc than the capacity. And this makes sense, but it can be a bit limiting. For instance, you can't just arbitrarily add flows together. You have to check if that breaks the capacity limit. And you can't scale a flow up and down. So if you have a flow of a certain value and it's too much, well, you can always move that down. But if you're doing it the other way, it might not be a flow anymore. The question might be, what is it? Well, what would be nice? What would be useful? We could always add and rescale flows. By rescale, we mean multiplying all the numbers, and we're only considering doing that by non-negative numbers. Really only positive, though multiplying by 0 is defined, it just makes it nothing. Obviously, we can't have negative flows because that doesn't make sense, because those are one-way roads. And there's always a way to return whatever these thingies are into real flows. And we can think about, well, if we scale things down, they fit, but we'll get to a reason why this is a separate bullet point. We don't want any flow to go across a 0 arc, and we'll see later why that's so important. Now let's just define these. Let's define these as unrestricted flows, or as I'll refer to them for short, uflows. Now let's define these things. So we want to keep the conservation constraint. And why is that? Well, the conservation constraint is that for everything except for the start and end, or the source and sink, we have the same amount of flow going into a node as out. And this makes sense because we don't want flow to magically appear or magically disappear or leak, as I called it. But we have a different kind of constraint instead of the capacity rule. Instead, we have no flow on a 0 arc. Otherwise, it can be any non-negative number. Now, why is that the case? Let's take a look at the whiteboard. So if I have a little simple network, and now this is before I've written any numbers down, you can already see that there could be paths like this, or like this, or like this. But imagine that this one has 0. Now let's think about this path again. How much flow could it carry? Well, it can carry at most the capacity of its arcs. But one of those arcs is 0. So that flow can't be anything beyond 0. In fact, it's almost like that arc wasn't there at all. Now, it is technically there. We'll see that there are some times where it is useful to consider, but it's very clear that we don't want this, because no matter how small these are, we can always scale our uflow down as long as they're not 0. So if this is 1 and this is 1, we could divide all these numbers by 4 and it all fit, except for this one. That's a problem. So we force this can't be 1, this has to be 0. Because the capacity constraint, that can't be 4, that has to be 3. So this should give you a good idea about why we have this rule about zeros. And you might be like, why would this even be here? Why is there even a 0? And the reason is, let's move over a bit and imagine this scenario again. mean, first we can get rid of this one because it's not going to be useful for anything else. Let's say we have one flow on this and one flow on this. And this one's a 1, this one's a 2. Well, we can think about, okay, what's left over? Well, there's going to be one unit left over here. We're going to erase this, but keep in mind that those are still real. In this step of the process, we're not including them. There was a 1 here, so now this is a 0. We don't want to actually delete the arc. We deleted the arc before because we were dealing with a generic case, but right now we want to keep this arc. We don't want to consider paths like that because it has a 0 arc, and hence no flow can go across it. So we only want to consider right now paths like that. Now, these aren't the numbers of the original network. What we're doing here is we're talking about the residual, and the residual is what's left over after a flow. Let's say we're gonna just omit all the zeros. So let's say this is our flow. It's 1 there, 1 there. We can think about, okay, all of the other blue numbers are zeros. We can talk about the residual because if we make that other network, if I put another flow on this network right here, the residual after it, I can add this flow to it and it'll work on this one. So we subtracted flow, and now, but if we get a flow on this, we can add these flows, and this is actually part of the algorithm that I was describing earlier. I didn't really go into it much, but you can think about, there's this sort of concept of when we're removing space, we're using up space and we're making these residual networks to represent what space we have left to expand into. Now, this doesn't totally work right when you have uflows and other loads, but we'll get to how we adjust this concept. Now that we're back from the whiteboard, let's take a look at another concept, this one of utilization. There's a lot of great things about uflows, but there is something we lose, and that's the physicality of it. If we find a uflow that has a value that we want, but it's putting 100 liters a minute through a 1 liter per minute pipe, it's not really as useful to us as one that does the same thing but is closer to a flow. And utilization is how full a network is. We can express this symbolically as well, but I'll get to that. So we can compute the utilization of a uflow, combinations thereof. Anything that is describing a load on a network is valid. And if it's less than or equal to 1, the flows or whatever fit inside the network. And now let's just go ahead and quickly think about how we would define this. Well, we want it to be the maximum of something, right? Because of this last thing right here. If any of the loads are bigger than the capacity, it clearly shouldn't be less than or equal to 1. So we want it to be the maximum of something. And we want it to be over arcs, but we want it to be over arc such that the capacity function is not 0. The other name for the numbers are weights. So I use W. This is to avoid confusion with C being for cut sets, though you could imagine just having a C there and it's okay. So you want the weight of the arc to not be 0 because it's kind of ambiguous because there can't be any load on it. And we want to know, let's set the load on the arc over the weight of that arc. We think about this for a moment and we can realize that this is actually a really good definition, because if the load is always less than the weight, then this fraction will always be less than 1, or less than or equal to 1 if the load could be the weight. Let's say that this maximum is greater than 1. Let's say it's 2. Then imagine we divided the load by 2. So let's say load prime of A equals load of A over 2. Then, if the utilization of this load was 2, the utilization of load prime, all of these are half of what they used to be. So the maximum is half of what it used to be. So that's why utilization is so useful. It works with scaling in this way, and we can flip between problems of asking about maximum value given some ratio versus set values, but trying to minimize utilization. Because if we can imagine, if the utilization is a half, we can double everything and still have it fit. So this is very useful. The other way to think about utilization is in terms of time. The reason why we can think about utilization in terms of time is that things don't carry just a set amount. They carry a set amount over time. A road can carry so many trailers per hour. A subway system carries this many people per minute. All these sorts of things. If a subway carries a person a minute, how many people can it carry in an hour? 60. This would be a really bad subway, but how many does it carry in 10 minutes? 10. So you can think about utilization is how much time to have all these flows happen if all of your capacities are rates. Then the utilization tells you how much time it takes. So now we can think about a new problem. Well, what do we want for this new multi-flow problem? Well, we want to minimize utilization. We want to find the fastest answer, or the one that fits the best in the network. But this would be trivial if we didn't have a few more conditions. So let's think about those. We'd love a condition that makes sure that we're getting things in the right ratios. And one of the easiest ways to think about this is an RC car factory. We need a certain number of wheels, we need a certain number of bodies, we need a certain number of controller units. And we need 4 wheels, 1 controller unit, 1 body to make an RC car. Well, we surely don't want to have it be that gives us hundreds and hundreds of wheels per car body. All those extra wheels are going to waste. So let's think about how would we do that, given that whole time thing, and say, let's minimize the time to make 1 RC car. Well, we clearly also need the wheels to get from where they are. The value is fixed. We need 4 wheels, 1 body, and 1 remote control unit. And they must start and end at fixed points. You need the wheels here, you need the bodies here, you need the control units here. And they all come from different places. So how are we gonna solve this? Well, we're gonna back up a little bit and think about a detail that we sort of